So student, good evening. So today, in the previous class, we already discussed about how to obtain, in fact, we defined the two type of force. That is, one is the step force and another is the impulse force. And they give some kind of transient response. So in the previous class, we gave some general expressions how we can able to obtain the response using transfer function. Today we will again explore the same concept, but we will derive a general expression for in time domain, which will be useful for finding the transient response, and then we'll take up some examples so that the concepts are more clear. In between, again, I will stop. If you have any query for that, then you can ask questions. If you have any questions in the previous thing, then maybe you can email me. I think some of the students had questions. They asked me through email, so you can ask me through email also. That will be a good way to communicate. So I'll show the slide so that we can see the next session. So today we will see the Duhamel integral. Duhamel integral or the convolution integral, and another name of that is. So this integral helps us to find out the response of a system, especially we'll see that for single degree of freedom system, spring, mass, and damper system, how we can able to find out the transient response of a system. So in figure you can see that this is the time axis and the force is the vertical axis. So force is varying in some pattern, and we have the force in the functional form. So we can able to define at what time this particular force will be having what magnitude. So let us say at time or tau, we have the magnitude of the force as Ft. And here if you see this force has started at time t is equal to 0 with F within bracket 0 magnitude, but at t is equal to tau is having F tau magnitude, and after this small time duration delta tau, change in the force is delta F tau. So you can see this is the change in the force during a small time. So this particular change in the force for a small duration we'll assume as that there is a step change in the response, change in the force, and we'll try to bring the concept which we learned in the last class, how we can able to find out the response due to this small change in the step force, and then we can do summation of such all step forces. If we divide this whole force region into small steps, then we can sum them up to get the total response of the system. So let us see that as I mentioned, we already defined during this delta tau time, the change is delta F tau, and we are considering this as a step function force of magnitude delta F naught, which is applied at time t is equal to tau, which is very important. So at present we are just focusing on one step force of magnitude delta delta F tau, which is applied at t is equal to tau. Other forces at present we are not considering. We'll consider them subsequently. So, what is the step or the indicial response which we derived in the last class? So unit indicial response was G tau minus T. So where the force was applied at time T is equal to tau. So this is for unit force. Now what is the step force we have? We have force delta F. So if we multiply this unit indicial response with the magnitude of the force which we are talking about, which is taking place during this delta tau time, will give us the response contribution during because of this force which has been applied at t is equal to tau time. So this is the response contribution from this small step. This can be written by dividing by delta tau and multiplying by delta tau like this. And if we sum up such small forces, then you can see this particular term. This is the same thing, but we have added the sign that indicates that small steps. If we divide the whole force, this whole force, if we divide into small steps, we will get the contribution in the response because of this small step force, and we have summed them up. So we are divided in different steps. Now at the t is equal to 0 also, there was sudden force F naught, but that force is applied at t is equal to 0. So this first term is corresponding to that we have the force magnitude, which is a step force at t is equal to 0, and this is the indicial response in which tau is 0. So because force is applied at tau is equal to 0, so we can see this is the gt, but they are applied at different time. So that is t minus tau. So xt is the total response due to this force. So this force has been applied to the system, and this expression 1.58 gives us the total response of the system due to this force, this arbitrary force, which we are in the functional form. Now, if this delta tau tends to 0, it is very small if we take the strip, then this summation will become integration, and limit will be up to a time we want to find out the response. So let us say this is the time t at which we want to find out the response. So we can integrate from 0 up to that point, and this delta will become differential, and this is the same expression, but with delta tau tends to 0, so we have the integral form. So this particular expression, which is we obtain in terms of indicial response G, and there is a integration involved. So this is called convolution integral or the Duhamel integral. In the next class, in the previous class, we have seen that this indicial response, which is due to the step force, we related with the impulse response, which is due to the impulse force. Now we'll try to convert this equation into the impulse response form, because that is more convenient for the solution of this. In the previous class, okay, so this is the same equation, the previous one which we derived, this one, 1.59. So we are doing some more mathematical expansion of this. So especially the second term, we are doing integration by parts. So first term is as it is. So integration by parts is how the integration of first part, that means f tau, then the differentiation of the second part, the second part will be as it is, and limit 0 to t. So integration of first part, second part as it is, limit 0 to t minus integration, the integration of this and differentiation of this. So differentiation of this with respect to tau. Okay, so this is the integration by part. I hope you must have learned in your mathematics course in earlier classes. So now this first term is as it is. Second term, if we substitute the limits, so this will become tau, tau will become t, and this will become 0, because once we put the tau is equal to t, this will become g naught minus, and then if you put the second limit, t, tau is equal to 0, so this becomes f naught, this becomes gt. So we have just put the limit in this to get these two terms, and this is as it is. I think here it should be positive, negative, positive. This should be negative, so that once we differentiate, then I think this should be negative. Sorry. Correct this so that things will be, this will be negative, and when we differentiate this with this, because this is a negative tau, so this will become positive. So finally, you can see that here some terms are getting cancelled. So first term and the third term are getting cancelled. So the second term is this one, and the last term is with negative sign or differentiation, I think will be this positive. Okay, this is fine. This is fine. Okay. So yeah, so here the prime represent the derivative with respect to tau. Okay. Now we know that the differentiation and integration can be interchanged. Order can be interchanged, so that thing will be applying during this. So this particular expression we obtained earlier, which we represented, this is due to the GT is due to the step function force, and this is due to the impulse. So in the last class we related these two. Now we will be using them to convert the convolution integral, which we derived in terms of g, to find out the convolution integral in terms of h. So this equation now we are rearranging. So this term I'm keeping in the right side. This I'm bringing in the second term I'm bringing this side. So you can see that this is negative. It is negative. Change. Okay. I think there is a sign change here, so no problem. I will correct this. So here, basically, what we are doing it now, we are now replacing the time t with t minus tau. Just change a variable. We are doing it so that when we differentiate, if you want to change the differentiation of this, so this will be d t minus tau will be minus t. So you can see this t minus tau, this. So we have replaced t with t minus tau, gt delta t. T has been replaced by t minus tau. So wherever t is there, we have replaced by t minus tau. And when we expand this, okay, when we expand this, so this is the same or derivative with respect to tau, t minus tau. Tau, this Prime is nothing but the derivative. Here I have represented prime is nothing but the derivative. HT is as it is, and GT is this thing. I would like to change here so that the things are okay. This should be negative, this should be positive. That is, you can see. So this looks fine now because we change this that side, so this becomes negative, this is positive. This also should be changed then. This should be positive, this will be negative. Okay. What is consistent? Okay, so why we are trying to find out this? Because again, I am repeating what I am trying to do here. I am trying to relate the response due to the impulse and response due to the response due to the step function and the response due to the impulse. So the convolution integral which we obtained in the previous slide is this. So we want to replace this with the h. So now we obtain that particular derivative term in terms of h. So now we can substitute this here. So we started with the relationship between the inertial response and the impulse response, which we obtain the derivative of that, and now we are replacing here. So basically you can see this is the same first term. Second term I have replaced g prime t minus tau with this. So this is that term into f tau and t tau or d tau. So now I'm rearranging this. I'm expanding this term. I'm bringing f tau inside. So that is the expression. Then now bringing the integration also inside. So you can see this is the first term as it is. This is because it is having direct delta function. G naught is constant, so this will come out from the integration. So only function is the f naught. So we have seen that the direct delta function property, this function, this integration of the function will be if we replace tau with the t, so that will be integration of the function. So integration of this, because this was constant, so it will come out, and integration of these two terms is nothing but this using the property of the delta or direct delta function, which I defined during the definition of that. So now you can see this third term and the first term is common, they will get cancelled. So we are left with the convolution integral in terms of the impulse response h, like this. So h, this is the response of the system. This is the force which we have defined earlier, which is changing with time. This is not periodic, is a periodic function. This is the impulse response this is the unit impulse response due to the impulse at time t is equal to tau. Okay, so this is another form of the convolution integral. Which is in the form of the impulse response. Now we'll see this is the same expression, convolution integral from the previous slide. Now, if we let us say change the t minus tau to another variable, lambda. So if we are changing to lambda, the limits will get changed. So when tau was 0, or here lambda will be p. Similarly, when tau is equal to t, from this expression, when tau is equal to t, lambda will be 0. And the differentiation, if you differentiate this, so minus t tau will be equal to lambda tau. So if we substitute this in the convolution integral, so here I have substituted in place of lambda. I have put in place of this tau, I have put t minus lambda. I think this should be t minus lambda. Okay. So tau you bring this side, so this will be t minus lambda, and this becomes a lambda, and t tau becomes minus d lambda. So if we simplify this, you can bring the h in the first, f in the second. Okay. Here, this negative sign has been taken by changing the limit. So limit, you can see it was t minus t to 0, t to 0. So that has been changed. So that negative has been taken there. So the final form of the convolution integral is this after the new variable, because this is this dummy variable. We can able to again switch back. So lambda, again we switch back to the lambda tau here. So this was the final form in the lambda form. But again we replace lambda with tau. So you can see we replace lambda with tau. So this is the another form of the convolution integral. If we see this expression and the first expression, so you'll see that they are symmetric in the excitation ft and the impulse response. So here f tau is there, here f t minus tau is there, and here h t minus tau is there, here h tau. So just the flipping of these two things are taking place. So that shows that they are symmetric in terms of this excitation and the impulse response. So these are the various forms of the convolution integral which we'll be using it for our purpose. So this is just graphical representation of the convolution integral. So you can see this is the convolution integral in which we have the force. So force can have some form, any form. It can be linear or any other form. So this is the force. Impulse response, let us say, for a particular system is like this. At T1 is having this value, because we want the multiplication of this h t minus tau. So what we are doing it, we are adding, because this is the h tau, so we are adding first t1 to this. So if we are adding t1 to this, that means we are shifting the impulse response toward the left side. So this is the t1 value. So we are shifted toward the t1. So you can see t plus tau plus t1 is there. So it's shifted toward this. Now we are folding it. That means we are saying this negative, the tau is this side is negative and this side positive. So we are flipping it. So you can see this is the mirror image of that. So here the tau is negative now. Here it was positive. So we have folded this. So this is the required form of the in the convolution integral h t minus tau. So now it has come. Now this and force we can able to multiply at different time, and we can add. So if we multiply this, we get this form. You can see the force is not there at the 0. So corresponding to this, all the terms will be 0 here. But these are the multiplication of the force tau and h t minus tau. These two multiplication graphically. And then response is what? Summation of all of them. So if we sum them up to some time t1, this, so that will give us a point on this response versus time graph. So this particular dot will be the sum area of this curve. So if you want to find out response at some other time, again we need to repeat the process. We need to shift by t2, then change this, then multiply this with that, again we'll find another area, so that will give us the response at some other time t2. So like that, the response can be obtained for this force using the impulse response function, which is graphically represented using the convolution integral. The convolution integral derivation I showed earlier, I started with the step function, and then I obtained the convolution integral using the individual response GT. But there is another way. Directly we can able to obtain the convolution integral using the impulse. We can, like, this is the force variation, same type of force. So instead of step function, we are seeing at t is equal to tau, this rectangle thing is the impulse which is applied at t is equal to tau, and duration of that is delta tau. So this is the impulse, and magnitude of the impulse is the f tau into delta t, because impulse is defined as the force into the time duration, which is applied for this particular case at t is equal to tau. So this is the impulse, one of the impulse. And similarly, we will be having other such rectangles. So we can think of this force as series of impulses, which is applied to the system. And from impulse response, we can have unit impulse response, we can get the response of the system. So this is the impulse which we obtain here, and this is the unit impulse response which we defined earlier. So this is the unit impulse response, which is the impulse is applied at t is equal to tau, as for this case. So this is the response because of this impulse, single impulse. Now, if we integrate all such impulses here, you can see that this will be the total response. Okay, and if you see, this is the convolution integral which we derived in the previous slide, which is exactly same, and which is much easier. Directly we can able to get the expression. Okay. This convolution integral is only applicable for linear system. Why? Because what we are doing it, we are taking one impulse, then obtaining the response, then we are applying another impulse and obtaining the response, and then we are adding them. So only basis based on that we can add is linear system. Non-linear system, the superposition theorem is not valid. So this is valid for only the linear system, but we can able to get the transient response from for various kind of force, blow, step function, impulse, or any arbitrary force, but we should know the functional form of the force. Okay, so only limitation is it should be applied to the linear system. So I think I'll stop here. I'll take some questions, and then I will go for, yeah. So Patel.
Yes, sir. Sir, in the second slide, at the time of bypass integral, there should be plus sign. Okay. But just first step was in the first step it was minus, but it should be for plus at everywhere.
Okay, I'll just check it.
Okay, sir.
I'll show the slide. Okay.
Okay, sir.
Show the slide. You can point out so that everyone can see that.
Sir, sharing is all on. Just you have
sharing is on.
Open. Yes, sir.
Okay. Yes. So which slide you are talking about?
Sir, not about. Yes, sir. Just in this.
Here,
On
huh?
no, after this one.
Okay.
On 28th.
Yeah, this is the
Yes.
28.
On integrating equation 1.59 and then after that point, because we have integrated g of t minus tau with respect to tau, so 1 minus will there.
Okay, so you're saying
And minus minus will plus.
this will become plus.
Yes,
This
sir.
will become plus. Okay, I got confused there. Then rest of the things will be changing accordingly.
So rest of the things were already correct, just here
Okay.
was only.
Okay, I think here there was change. Okay, any other question?
Not now.
Any other?
No, no, sir.
Let me
Thank
ask
you.
any other student. Any other question from any other student? No. Okay. So I continue with the same discussion. I think now most of the mathematical thing we have taken care. Now, yeah. Yes. Now we'll take up some system, because at present the previous slides I was talking about in more general. Now I'm taking a single degree of freedom system, and we are trying to find out the transient response for that. So here also, in some way, it is more general or specific. I think finding the response we will take up in the form of example. So here you can see that we are applying a non-periodic or aperiodic force to the dynamic system. The dynamic system is single degree of freedom. At present, this is undamped system. So single degree spring mass system is there. We have specified the initial condition x naught and v naught. So this is a typical uh, free vibration. I think expression you must have studied earlier, or in the I think the second class I described. Xt is equal to a sine omega nft plus b cos omega nft. So a and b have been obtained based on the initial conditions. Okay, so these are the V naught and A naught have been used to calculate those A and B, and here A and B is replaced with this initial condition. Now this is the response of the system for a particular initial condition, but initial condition will be specified by the either what kind of forcing we are giving or what kind of system is this. So if we are saying the impulse if we are applying to the system, this is defined as summation of the force with time, and because Newton's law says that force is nothing but the mass into acceleration, where mass and this is the acceleration in terms of velocity dv by dt. So if we take the dt this side, ft, f dt, so the right side becomes mv. So this is the impulse. So again, this change in the velocity, dv is nothing but the change in velocity due to this impulse. So this is the change in velocity, which we can able to write as f dt by m. And I'm writing the f dt, which is impulse, as f cap, or like this. So this is the change in velocity due to the impulse. I'm not sure whether you can able to see the initial, yeah. So now the velocity, what is the initial condition? Velocity, this, because of the impulse, we have v naught is equal to f naught plus m. So let us see the system was stationary, spring mass temper was stationary. We applied impulse. So at t is equal to 0, it will be having this velocity because of the impulse, but initial displacement was 0, so that is 0. So you can see how we have converted the impulse force, how it will give initial condition to the system. So this is the initial velocity. Because of the impulse, suddenly the body will be having this much velocity, but displacement will be 0. So okay, in the previous slide, if I show, if I put the whatever the boundary condition x0 0, x0 0, that means this term will not be there. V0 is f cap by m. So this is the term in the next slide. So f bar by m omega n f. First term is 0 because initial displacement is 0 because of impulse. So now you can see f bar is as it is. Rest of the terms I am representing as ht. So this is the response due to the impulse, which is given as unit impulse response. This is the response due to unit impulse, and at present the impulse magnitude is f naught, f cap. So if we multiply with the magnitude, obviously we'll get the response of the system. So ht from this expression is this, which is unit impulse response for single degree of freedom spring mass system. So this is explicit expression for the single degree of freedom system, spring mass system without damping. Okay, now if you remember, we are trying to find out the same thing using the Laplacian thing. We obtained the transfer function earlier like this. This was the expression of transfer function. How we define the unit impulse response? Inverse Laplace transform of the unit impulse response function in this Laplacian domain. And what was that? That was GS. So GS is given like this, but damping is also here. So if we ignore the damping, the expression will be, this term will be gone. 1 by s square plus omega nf will be there. There will not be zeta term. So that is similar to this expression. Okay, so GS is this without damping case. So if we do the inverse transform of this, again I can show this inverse transform of this, because there is no a term here, so there is omega here, omega enough. So I'm dividing and multiplying by omega. So this is the standard form of this inverse Laplace transform. So this will give us the sine omega t. I think there should be omega t. So here I think it should be omega t, which is, then if you see this expression and this expression is same. So either we are using the concept of the impulse initial condition or directly using the Laplacian domain, we can get the similar expression for the unit impulse response for single degree of freedom system. For damped case, we'll see subsequently. So I will take up one example now to illustrate how this can be useful to us. Okay, so here we are taking a single degree of freedom spring mass damper system. There is no damping in this, but this is the force pattern. So suddenly we are applying a force of magnitude F0, and then it remains to the system forever. In the previous slide, we already obtained the unit impulse response function like this. Okay. Now we'll be using the convolution integral to obtain the response to this force in a spring mass system. So this is the convolution integral, where this is the our impulse response function, This is applied at t is equal to 0. So we need to replace that when we are applying at t at tau is equal to at t. So you can see that magnitude of force is constant. So F naught and the impulse response function I'm writing as it is, but here this t minus tau and integration with respect to tau. So now we need to integrate this. So constant term will come out. This will be cos minus here, okay, minus omega, limit 0 to t. And if you put the limits, I think you can able to do this. We will get expression like this. So here, because omega nf is nothing but omega nf square is nothing but k by m. So if we replace with that, we can able to get the I think k here, f naught k 1 minus cos omega t. So this is the response, which will be which is the functional form. We can able to plot them and see how the xt, the mass will be vibrating because of this force. So this is the response. So you can see there are having two parts. One is the constant term f naught by k, and another is the negative f naught k cos omega t. So this is the second part. Minus should be there. So second part of this, so you can see this is the cos function, but negative sign. So it will repeat after this. And if we add the constant term, so it will shift toward the upward. So this is the final plot. The second plot is the final plot, in which so is like this, and then it will repeat. It will repeat like this. So this is the response which will be there because of the step function which we have shown in the previous slide. Because there is no damping, so this pattern will repeat forever. And we can able to see the maximum amplitude of this from here to here. That will be twice of f naught by k, and minimum is 0. Okay. Minimum is 0. So maximum and minimum we can sometimes be, that is very important key, because of the machines, some spacing to be provided. So what will be the maximum displacement can take place. So this information will be useful for that. So this is clear. Okay, how we can able to get the response or a general force using convolution integral. Okay, I'll take up another example. So in this, the force is changing like this. So force is up to first 3 seconds, there is no force. Then suddenly the magnitude of 10 Newton is applied, and it remains up to 6 seconds, and then again drops to the 6, and then it remains 0. So if you want to find out the response of the system, so we need to have three parts. First is what is the response during 0 to 3 seconds, because there is no force between this period. So obviously response will be 0. Okay. So here in the example, all the property like stiffness, K, C, those things are given. Okay. And this is the force pattern. So up to 3 seconds, there is no response because there is no force. But after 3 seconds, there is a sudden force. So during this period, maybe you would like to know, okay, at 4 seconds, what is the response, or 5 seconds, what is the response. So in the second part, from 3 to 6, we need to find out what is the response at intermediate positions, not at the end only, but at intermediate positions also. So the second duration, this is during T1 and T2, when we are applying a force magnitude 10 Newton, then how we can able to get the response. So what we are doing, we are saying T1 to T can take 3.1, 4, 5, whatever we want. So we are trying to find out the response in terms of t, and depending on the where at what time we require between this duration, we can put the value of that. T1 is 3 because the force is started applying at 3. So here this is the convolution integral. Integration is very important here. The limit T1 to T. We are not doing T1 to T2. T1 to T2 means then it will be directly giving response uh, at this location at 6 seconds. But if you want to obtain intermediate, then we need to put as T. Then we can able to put the value of that because there is a constant force. So F force will be there, and is already the HT, the impulse response function has been given here, which we derived. Okay, 1 by omega t. So already the HT we have substituted here. And only thing now we need to integrate this between T1 to T. So once we integrate, here you should be very careful. We are integrating with respect to tau here. So we should put the limit for tau, not for t. So there is some confusion you may get here. So like you need to put this limit for tau. Then t minus t, this will become 0. T minus t1. Okay. So this limit has you need to put for the tau that is to be taken care. So finally we'll get this kind of response. So here you can see this is in terms of t. So we can take t from 3 to 6 any value. Okay, so but we cannot take beyond that. We cannot take 7 for this expression because we have taken care of the force up to 6 seconds. So t will vary from 3 to 6 depending on what value we want, or if you want the variation of this for different value, we can get the value of xt and we can plot. Then what happens after 6 seconds? 6 seconds, t is greater than t2. So here, okay, so this is we have no force after t2. Okay, so and before t1. So limit has been taken from. So only force if I'm talking about, if let us say if we are applying, if I want to obtain the response at 7 seconds. So for that I need to consider all the forces before that, including 0 to 3 there is no force, so no contribution, but from 3 to 6 whatever the force, that also I need to consider because the contribution of that will be coming at the 7 second also. So this point I hope is clear that if you want beyond 6 seconds, that is a 7 or 8 seconds, we need to consider all the forces contribution to the response in the integration. So here we could have taken 0 to T1 integration, but because force amplitude is 0, so that is 0. Then the second term is T1 to T2, T1 to T2. Third term should have been this T2 to T, but the force is 0, so that is not contributing here. So that means after 6 seconds, whatever the response will be there, that will remain same. It will not change because there is no additional force applied. So this is actually we should have taken 3 terms, but first and the third terms are 0. So only the second term has been considered here. And if we integrate this, we will get this expression. So there is no additional force, but with time, because of this cyclic nature, they may vary. Because this t is already there. So when we when the limit we are putting for tau, not for t. So this is the xt variation of the response. If you want to find out beyond the second t2, this expression should be used. So there are three things. One is the before this 0 response, 3 to 6, the expression 1 should be used, and beyond 6, the expression B should be used for plotting the response. Okay, if any questions, I think people can ask. I'll take some more, one more. I'll give the derivation for the impulse response function for the damped case, and then I'll give some exercise problems. Any questions on that? Okay. Huh. Yes.
In the second slide that someone was mentioning, I think the minus sign only comes once. Check that, sir.
I will check it and I will let you know. I think I'll check it. I'll check it. Any other thing? Okay. So this is the damped system.
Sir.
Yes, please.
Sir, in the second example, can you please explain the limits, how we have taken those limits of T1 and T2?
Okay. First, this one or the third one?
Sir, the undamped one. The just this one.
So which one? The second part or the third part?
Sir, the second part.
Second part, no? So
yes.
Second part, I'm saying the limit is because maybe I want to find out the response in between also from 3 to 6. Okay. So what I will be putting the limit, because force change has started from 3, T1. Okay. And now it can change up to 6. It is changing up to 6. So if I want in between also, so that's why I've taken T1 to T. And T can take any value from 3 to 6.
Okay.
Any value between 3 to 6. So the expression is containing T. Now I can, if I would have taken T2, then this is the total response at when at T is equal to 6. Okay. So this is in the variable form. Now I can use this expression to obtain response in between 3 to 6 any value. Clear?
Yes, sir. Yes.
Should I explain the third part also?
No, sir. Thank you.
Okay. No issue. So quickly, I think, in case, I think you already know when the damping is also there, the response is something like this, which for single degree of freedom damped case, the exponential term, decay term, or under damped system, two constants C1 and C2 is there. So here I was just given the how to obtain the constant C1 and C2. So because the initial condition will be x naught is equal to at t is equal to 0, x naught, and velocity v naught. So these are the two initial conditions. Because we need to require the velocity also. So if we differentiate the first with respect to time, we will get the long expression. We can able to do it. So this is the differentiation of the first. Now I can substitute the initial condition first. This is for displacement in the first expression. So this is for the first expression. It is giving us C1 is equal to x naught. Then the second expression, velocity. So if I put t is equal to 0 in this, and that is the velocity v naught. Okay. So if we simplify this, this is giving v naught is equal to this. From here, because C1 we already obtained is equal to x naught, C2 can be obtained. So this is the application of the two initial conditions to get the C1 and C2 in the free response of the dam system. So C1 and C2 we know. We can again put back here C1 and C2 or whatever the value we obtain. So that is the last expression is that. So we have already replaced the C1 and C2 with the x naught and velocity and initial velocity and initial displacement. Okay, so now how we can get the initial response. So this is the same expression having initial displacement and velocity. When we are applying impulse, we know V naught is given by this impulse divided by mass, and x naught is 0. This we already seen when we apply the impulse. This is the initial condition. So we can replace V naught by this here, and x naught we can keep as 0. So if we put this in this expression, you can see x naught is 0 means this term will go, or this term will go. V naught by W or omega will be left out. Okay, so this is the expression we left out, and here we can able to put the V naught as this value, like this. Okay, so you can see now again I'm writing HT into F bar. F bar is this. The remaining term I am saying is HT, unit impulse response. Now this HT is including the damping also. So there is no damping. We already saw that this term was not there, but with the damping, this is the additional term. Okay. So this can be used in the damped case. Only difference will be the expressions will contain slightly earlier we differentiated the cos and sine only, but this term also will be coming exponential. Okay. So this formula will be useful. So there is no need to do integration. Just this formula you can use because this is a closed form formula is available. So like if you have this kind of expression containing exponential and sine, so directly you can use this formula and you can get the expression. There is no need to derive. So this is the thing I want to. You can use this. Or there is another way you can obtain. You can write sine in terms of exponential, and you can integrate. So either of these two formula you can use it to find the this integration. So this is the two problems I am giving as an exercise. Maybe you can try out. So first one is a single degree of freedom undamped case. So force is waning like this. At T naught is becoming 0. At T is equal to F naught. So linearly is varying. Okay. Or it is decaying. And in second case, it is linearly increasing up to T naught. Then it becomes 0. Okay. So first one is for undamped case. Second one is for damped case in which the previous potential response you need to use this one. So additional complexity in the form of integration will come, but procedure will remain same. Okay, so this anyway will be streaming, so you can able to see this by evening. So generally, if I give some assignment by 1 week, you should submit this. Any questions on this?
Sir,
yes.
Along with video, can you also upload these slides which you are showing to us?
Okay, actually, because I am updating the slide, so that's why at present, once I complete the chapter 1, then I will upload with all the corrections and other things. Because I'm doing the slides first time, so here there plus minus signs, all those things are there. So once I complete the first chapter, which I have now already completed, next lecture I'll be taking on the second chapter. So now with all these corrections suggested by student, I will upload this. Okay. Yeah. So in the first chapter, actually, mainly the single degree of freedom system is there. Whatever now is remaining, in some form you already studied, so I'm not repeating that. because the focus of this particular course is multi-degree. So now I'll switch over to the second chapter. I've already suggested to, I think, see the NPTEL lecture regarding the logarithmic decrement and that kind of thing. So I'll not repeat those things here.
Yes.
Yeah. So with all these corrections, I will upload the PDF of this PPT.
Okay.
Yeah. Any other question? So you try this exercise, which I have given two exercise. We'll explain how you'll uploading the. You need to upload those as exercise. Once you need to take. We'll tell the procedure how you'll be uploading it into the some site. We'll give the detail of that through email. So any other question? Okay, I think